Yeah, we are now getting to the more interesting parts of this lecture, and in this video we are going to talk about empirical confidence intervals using the bootstrap method. So recall we already used the bootstrap method previously when we talked about ensemble methods. So that was one part of the bagging method where we drew bootstrap samples of the training set. So where does the bootstrap name come from, by the way? So the bootstrap, the physical item, that would be the strap of a boot, of course. I tried to look it up. So here I'm just quoting around 1900. It meant basically to pull oneself up by one's bootstraps, which was figuratively used as describing an impossible task. So if there's something really challenging, so here we are trying to estimate the sampling distribution from a sample. So that's kind of a tricky thing to do. So here we're trying to pull ourselves up by our bootstraps, just meaning that we do something difficult. So here later on it was also its meaning expanded to include better oneself by rigorous unaided effort. So nowadays there's also a political meaning of pulling oneself up by one's bootstraps, but I don't want to talk about politics in this class. So here we are just thinking of the bootstrap method of doing something that is quite tricky, and we are doing it anyways. So in this context, I actually added a lot of text here. It's also just to remind myself what to talk about, and so that you also have that for reference when you look at the slides later for studying. So the bootstrap method is a resampling technique for estimating a sampling distribution. So our problem is that we only have one data set. And how do we make use of that? So we can use the bootstrap method to resample that data set, and we can use that to estimate the sampling distribution. In particular, what we care about is estimating the uncertainty of our performance estimate. So we can use that to estimate the performance of our model, but also the uncertainty of it, so confidence intervals. Originally, the bootstrap method was introduced by Bradley Efron in 1979, a long time ago. So here's the paper if someone is interested in reading that. Then about 15 years later, Bradley Efron and Robert Tibshirani wrote a whole book on the bootstrap. So it's called An Introduction to the Bootstrap. Quite a thick book, so if someone is interested in that one, here's the name of the book, so you can find that online. In brief, the idea of the bootstrap method is to generate new data from the population by repeatedly sampling from the original data set. So we don't have access to the population, but we kind of have a workaround using the sample, so the data set that we have, and we sample that to kind of simulate drawing samples from the population. And this is sampling with replacement, as you recall from the bagging lecture. In contrast, the repeated holdout method that we talked about in the previous video is a sampling without replacement, because in the holdout method, when we have a data set, we shuffle it and then divide it into two halves, or 80 and 20% or something like that. So let's say we have 50-50, but then there's no duplication of any data points in this data set. We just split it, so you can think of it as a sampling without replacement. Whereas in the bootstrap method, as you recall, we can have multiple instances multiple times in each of the bootstrap samples. So using the bootstrap method, we can estimate sample statistics. It could be any type of sample statistic. So imagine you have like one sample of something, and there might be any statistic you're interested in. It really is open or up to you what kind of statistics you are interested in. Could be standard deviation, could be R squared, or correlation, or to some other variable, or whatever you like. And then what you do is you draw these bootstrap samples. So let's say you have the sample mean here. Let's write this as x bar or something like that. Let me use a different color. Say you have the sample mean as something you would like to study. So you have sample mean here. So drawing then these different bootstrap samples, you get different sample means, right? x2, x3. And If you would do that a large number of times, you will find that this will be a normal distribution. So the sample means will follow a normal distribution. For example, like this. And then the standard deviation or variance, or let's say standard deviation here. The standard deviation of the distribution of sample means would then be the standard error of this mean here. So recall from other statistics classes when we talk about the standard error of the mean, let's call that SE. We usually compute that from the sample standard deviation. Let's call that SD divided by square root n. So this usually refers to the standard deviation of the means, not of this mean here, but the distribution of means. If we would have multiple samples and we compute the mean for each of these samples and look at the distribution. So this the standard deviation of this population here, or distribution, would be the same as computing it this way. Of course, this is now with the actual data here at the bottom, whereas this one is estimated, right? So the bootstrap allows us then to construct confidence intervals because we know the standard deviation from that, so we can use that to estimate the standard deviation, so the standard error of the mean. But we do that here empirically. So in a nutshell, how does the bootstrap procedure work? So we have step 1, we draw a sample with replacement, then we compute the sample statistic, and we repeat step 1 and 2 n times. N is usually a number, so in the book they recommend 200, but usually the bigger the better. And then you compute the standard deviation. This is this one here, which is the standard error of the mean of the statistic. And then you can use that to compute the confidence intervals. So how do we now use the bootstrap method for evaluating the performance of a classifier? So think of the case we are given a data set of size n, and then we do B bootstrap rounds. And in each round we draw the bootstrap sample. So here is just a lengthy way of describing how we draw a bootstrap sample. The bottom line is that we draw samples with replacement until we reach size n, which is the size of the original data set. So it's just getting a bootstrap sample. That's nothing new. That is what we described already in the bagging lecture. And then we fit a model to each of the bootstrap samples. So we fit one model to each bootstrap sample, and then we compute the resubstitution accuracy. So the resubstitution accuracy is a fancy word of saying training set accuracy. So for example, if I have my data set of size n, I may have a bootstrap data set like this, bootstrap. It's also size n, and we use that to fit the model. So we have a model fit on this bootstrap data set, and then we evaluate the model. Let me use a different color. So then we evaluate it on the same data set, so the same bootstrap data set. And as you recall, this will be an over-optimistic estimate because it's like fitting and evaluating on the training set. But I'm just describing the original procedure here. So we will find a better way after we discuss this. So here at the bottom, this is the 0-1 loss. So it assigns a 1 if the classification is incorrect, 1 if incorrect, and 0 if correct. Oh, this is such an ugly handwriting. One second, let me fix this. 1 if incorrect, 0 if correct, and then we have the 1 minus here, so this would flip it around, so this will become 0 and this will become 1. So then this thing would be the accuracy for the Bth bootstrap round. So each bootstrap dataset consists of n training examples. So we just average over these correct predictions here. So this is the accuracy then. And then we repeat that b rounds. So we have b of these accuracies, and then we average over these, and this is then our bootstrap accuracy. So it's just averaging the accuracy over the different bootstrap rounds. Yeah, and like I said, or like we discussed many times previously, the risk substitution accuracy usually leads to an extremely optimistic bias, since a model can overly sensible to noise in a dataset. So the keyword is, overfitting is the issue here. So I was describing the original bootstrap technique, which was originally developed to determine the statistical properties of an estimator when the underlying distribution was unknown and additional samples are not available. So we tried in the previous slide to adopt this for model evaluation. However, yeah, like we said, there is this issue that we have overfitting going on here. So in order to exploit this method for the evaluation of predictive models, like we are doing here with the classifiers, or also for regression, we may want to modify this method. So we may prefer a slightly different approach to bootstrapping using the so-called leave one out bootstrap technique. I don't know why it's called leave one out bootstrap technique, because it's relying on the out of bag samples, but yeah, this is just the name for it. So we use here the out-of-bag samples as test sets for evaluating the model instead of evaluating the model on the training data. So instead of computing the resubstitution accuracy, we compute the accuracy on the held out-of-bag samples. So this is a lot of text and hard to parse. So let's take a look at the visualization. So this is the visualization about bootstrapping that I showed you in the ensemble methods lectures. So here, the original data set, and then we have different bootstrap rounds, and recall that some items may be duplicated, right? Because it's sampling with replacement. So some items may be duplicated in each round, and if all of them are size n, this is size n, this is size n, and this is size n, and this is size n, and if we have duplications, that means that some items or some training data points from the original dataset can't be included here, right? Because otherwise it would be larger than n. So what happens is that there are some examples that are not part of the bootstrap sample, right? So these are the so-called out-of-bag samples, and we can actually use these out-of-bag samples to evaluate a model. So what I mean is we can fit the model on this part, on the bootstrap sample, and then use the out-of-bag here to evaluate the model. That would be fairer because the model was or has not seen these examples when it was fit on this data set. So this would be the leave one out bootstrap. I don't know why it's called like this, but it's call it like this. Okay, so and this is how then we can use the out-of-bag data points to compute the accuracy from bootstrapping. So here this is now based on out of bag examples, and then the average is the average is still similarly computed by averaging all these accuracies. And then we can compute the variance here with a square root. This would be the standard deviation of the distribution of the accuracies. So we will have a distribution of accuracies. This will be a normal distribution. So it's the distribution of the accuracies we collect from bootstrapping, and then this is actually because this is like the distribution of the means, right? So distribution of the sample mean. So this is then also actually what we call usually the standard error when we only take a look at one sample, right? So here we don't have to do anything extra. We don't have to divide by square root n in order to get the standard error. This is already our standard error. And then we can use a t-distribution for constructing the confidence interval. So this is a normal distribution, or if the sample size is very large, right? I mean infinitely large, but this is usually better approximated by a t-distribution, especially if we have small sample sizes. If we have large sample sizes, with that I mean repeating the bootstrap many rounds, then this will be identical to the z-value from a standard normal distribution. But in any case, we are considering a t-distribution here, And for the 95% confidence interval, we would have 1.984. Actually, this should be 0.025. Okay, because we're looking at a 95% confidence interval. 0.05 would be a 90% confidence interval. Okay, so yeah, this is how we can then construct the confidence interval for our bootstrap. So let's take a look at how we can do that in Python. So here we will be just using the iris dataset because it's simple. So we will be working with iris, test size 0.15. Actually, we don't need a test set for this approach. We can actually just use the whole dataset, but we will compare this method to some other methods like the normal approximation interval, which requires a test set. So which is why I'm creating a test set here. And we will be using a k-nearest neighbor classifier with k equals 3. Now here is the leave one out bootstrap that I discussed previously. So I'm going over it in code. So first here I'm bootstrapping the training sets just to construct these bootstrap accuracies. So if I go back 2 slides, what I'm computing here is I'm computing these accuracies here. So the accuracies for the B bootstrap rounds. So I'm doing it as follows. I set a random seed. Then I have this index here, which I use for drawing the bootstrap samples. And here I have a list. I call it bootstrap train accuracies. These are my accuracies. So when I have the 1 over B accuracy I, so it should be a sum. So these accuracies here I'm collecting in this list. So I do it 200 times. So B is 200. And each round I choose a random subset of the training indices. So that's the same size as my training set. However, it's with replacement. And then all the data points that are not in this bootstrap sample here will be the test data points. So here I'm just computing the set difference. So to get all the ones that are not included in the bootstrap sample. Then, so here I'm doing this with the indices, so I can get the corresponding features and labels for both. So here I'm doing this for the test and here for the train labels. So I get the data set. So here, if I go back a few slides, this one will be my bootstrap train set. And then this one would be my bootstrap test set. Okay, so I have my bootstrap train set here and my bootstrap test set. And then I fit the classifier on the training set here. And I evaluate it on the out of bag. So here's out of bag evaluation. And then I'm collecting the accuracy in my list. So the accuracy gets collected in this list. So at the end, the list should have 200 accuracies, right? And I can then also compute the mean, the average accuracy, which in this case turns out to be around 95.5%. So yeah, also you can find the full code here if you want to run it yourself with a different classifier or on a different data set. Okay, so now the confidence interval. So here what I'm doing is constructing the confidence interval using the equation that we talked about before. So this would be our mean bootstrap accuracy plus minus t times the standard error. Oops. The standard error, recall, is usually computed by dividing sample standard deviation by square root n. However, this is usually just estimating the standard deviation of the population, right? So in this case, we don't have to divide by square root n because we already have that. That one is the standard deviation that we compute from our accuracy distribution, which is computed by 1 over b, and then the accuracy for round I. So we do that for b rounds, minus the mean accuracy, right? Accuracy, let's call that accuracy mean squared. So this would be the variance, and then we would take the square root. This would be then our sigma. Also, yeah, I have it right here, accuracy minus the mean for all the accuracies that we have collected, squared. We're summing them up, then computing the average. So I should have put b minus 1 here, and then taking the square root. So that's our standard error. Then based on a t-distribution, we use 1.97 because we have 199 degrees of freedom here. So degrees of freedom is n minus 1 usually. So in this case, b minus 1. Yeah, and then we have both the lower and the upper confidence limits. And here I'm just visualizing it. So here, this is a histogram of our sampling distribution. So these are the accuracies. And here these two are the confidence bounds. So the mean, this is the mean here, mean accuracy. And this is the lower and the upper confidence bound. You may want to put that here at 100 because you can't have accuracy larger than 100, right? Okay, so this is one approach for constructing a confidence interval based on the bootstrap. Another one is the percentile method, which is, I would say, recommended in practice. This is especially useful if you have a small sample size and you find that when you construct the bootstrap samples, that the sample distribution of the mean doesn't follow a normal distribution, for example, because the central limit theorem is violated. I mean, it's the sample size is too small. It doesn't apply. The central limit theorem doesn't apply yet. So in this case, you can just use the percentile method. So how that works is that we pick the percentiles. So if we have our distribution, we look at the 2.5th percentile and the 97.5th percentile for a 90% confidence interval. So if I go back one slide, what we are doing is we are just taking a look at where's the line to be drawn such that 2.5% of the samples fall below here, and here that that 2.5% of the samples fall above here. So we are just looking at these percentile points. So this is the 97.5th percentile, and this is the 2.5th percentile. Okay, so when we do that, we can also construct the confidence level here based on these on the percentile method. And yeah, it turns out to be like this. So here we have the percentile, the upper and lower, the 97th and 2.5th percentile. I was using the NumPy method for doing that. So here you can see the confidence boundaries for the percentile method, and you can see they are very close actually. That's not very different here. So that would be another way you can get confidence intervals from the bootstrap. Yeah, and there's another method not involving fitting the model multiple times on these bootstrap samples. So another way is bootstrapping the test set. I've seen that in a couple of papers recently where the researchers bootstrapped the test set. So how does that work? So instead of just refitting the model, we just fit the model one time to the training set. This is especially useful if you work in deep learning, because models may be unstable, they may not converge. So we would have to spend a lot of time monitoring the bootstrap data sets and see if the models converge on all these bootstrap sets. And model training can be also very expensive in deep learning. So we usually want to avoid fitting the model multiple times. If you think of the GPT model, I think it takes multiple weeks or months to fit this model with the GPT-3, and I think it costs like $80,000 or $100,000 to fit the model, so you don't want to do this multiple times. Anyways, so predicting, you predict then basically on the test set. So here you get the test accuracy, and you're interested in, so this is the test accuracy in the confidence interval here. So what you do is you compute multiple test accuracies by bootstrapping the test accuracy. So you have the test set labels and you have the test set predictions. So you have y hat and y. So what you can do then is you can draw random bootstrap samples. So usually they go hand in hand. So for example, you have 0, 1, 1, 0. If we have a binary class problem for, let's say, y hat, these are my predictions, and for my true labels I have 0, 0, 1, 0, 1, 0. So you can draw bootstrap samples, so you draw the corresponding ones and you put them together in the bootstrap sample, and then you compute the accuracy based on the bootstrapped predictions and test set. So here I'm doing this based on an index again. So I have an index here, drawing it with replacement from an index array that has the same size as the test set. And then I'm computing the accuracy based on selecting with the index the predictions and the corresponding test instances. So for example, these 3 pairs, and then I could draw them with replacement. So maybe what I have is then 0, 0, 1, 0, 0, 1, maybe again 0, 0, and 1, 0, so 2 are repeated. This is then my new thing for comparison, for which I compute the accuracy, and I collect these accuracies, and then I can use again the percentile method to draw the confidence interval, so right here. So this would be then the confidence interval based on bootstrapping the test set. I think this is not really ideal to do that, but it's just computationally cheaper. So yeah, lastly, to end this video, I have a comparison of different bootstrap methods here for drawing confidence intervals, and also the normal approximation for comparison. So these two are methods we are going to cover in the next video, so ignore them for now. We will revisit them in the next video, so don't pay attention to these here, but the other ones. So here I have the percentile method, and here I have the bootstrap based on standard error, so plus minus, and this is above. You can see these are very similar, so they're very close, so it doesn't really matter, but why not just using the percentile method? It's usually a little bit more robust. And then here I have bootstrapping the test set, which is what we talked about in the previous slide. You can see the confidence level is a little bit larger. It's also computed completely differently because these are computed based on the out-of-back estimates, whereas this is based on the test set. So for this one here, we don't use the test set at all. Actually, you can have, in this case, a larger data set if you don't use a test set, because you could, instead of splitting the data set into training and test sets, you can use the whole complete data set. And here at the bottom, I have the normal approximation interval that we talked about in the previous lecture. You can see also this is very similar to bootstrapping the test set. Okay, so in the next video, we will talk about these additional bootstrap methods.